Right, so this is one of the videos on the physics topics. So I'm going to try and do the energy topic in 10 minutes, which is a bit optimistic, but we'll see how we get on. Okay, so the first thing I'm going to talk about are the different energy stores. So in this top left-hand corner, energy stores. The three most important ones that you have equations for are kinetic, and the equation there is a half mv squared. Gravitational potential, so I'm just going to write GPE, and the equation there is mgh. And the third one is elastic potential energy. So that's a half ke squared, spring constant extension. So these three you have equations for, and these often come up where you've got to calculate something, and they can even come up in the multi-equation questions where you're talking about 5 or 6 marks. Now, other important energy stores include thermal, so when things are heating up, chemical, foods, fuels and batteries, nuclear, and there are a few others, but I'm not going to mention them just yet. Okay, so when we're talking about these energy stores, we're usually talking about energy being transferred within a system. Now, in physics, when we talk about system, we're talking about an object or a group of objects. So these energy stores, it can be distributed between the different stores within this system. Now, the only other thing I wanted to mention is a closed system, which I'll write here. A closed system, which you often hear in physics, is one in which the total energy is constant. Okay, so it can change between all these different stores, but it will remain constant. And that kind of links to our conservation of energy. So that's the definition we all need to know, so I'll write that one here. Energy cannot be created or destroyed, but it can be transferred. So only transferred. Lovely. So when we're talking about these energy stores, there are a few examples that you need to be familiar with and you need to be able to explain. So one of the ones you need to be able to describe is when an object that's at some height, so if I just label that h, is dropped. Now initially it will have gravitational potential energy as a max because its height is at its maximum value. At this position its kinetic energy will be 0 because it's stationary. Now once it's dropped, what happens is your gravitational potential energy decreases because your height's decreasing, and your kinetic energy increases because your velocity is increasing. So if I just put below there, height is decreasing and velocity is increasing. Another example that you often see is when the ball strikes the ground. I'm just going to try to over-exaggerate this. The circular ball, spherical ball, might be misshapen. Now what's happened here is your kinetic energy, which it had because it was travelling at quite a large velocity, becomes elastic potential energy. Elastic potential energy is all to do with changing the shape of an object. Now what's going to happen after this is that ball is going to recoil and it's going to bounce back up. So that elastic potential energy will decrease, and that will be transferred to kinetic energy because it will have a high velocity as soon as it bounces up, and that will eventually be transferred to gravitational potential energy as the speed decreases and the height increases. Okay, so that's a little bit on those. We'll do some more of those in lessons. If you want any specific examples, you can come and ask me, or look on YouTube and stuff. So the next bit I'm going to talk about, still focusing on energy in these equations. What I'll do actually is I'll just put a little box around these. So anytime we've got an equation, we'll pop a box around it. The next energy that I need to talk about, and we'll do this in more detail in the particle model topic video, is this thermal energy. So objects, when energy is transferred to them, they gain thermal energy, and based on their mass and their specific heat capacity, so I'm just going to put SHC, which I'll do more on in the next video or so, this is going to determine what their change in temperature is. Okay, so if something's got a fairly low specific heat capacity, it doesn't require a lot of energy to change its temperature, so its temperature will increase by a lot. Other substances like water have very high specific heat capacity, so they require a lot of energy to change their temperature. So just on that, I'm going to put the definition down here for specific heat capacity. So that is the amount of energy required to increase, or actually it's to change, the temperature of 1 kilogram of a substance by 1 degree C. And I'm going to underline the 1 degree C and 1 kilogram. So you've got to be very careful that you include those. And there is actually a required practical for this. And what I'm going to do is separate videos for all the required practicals. Okay, so let's move on. 5 minutes, not doing too bad. The next thing I want to talk about is power. So there's 2 equations for power. Oh yeah, sorry. Put a box around that. Power can be energy divided by time, or power can be work done divided by time. So essentially, power is the rate of energy transfer. If something's got a high power rating, it means it will transfer a lot of energy. If it's got a low power rating, it will transfer a little amount of energy per second. So if we compare 2 values, 1 kilowatt and 8 kilowatt, we know that a kilowatt is 1,000 watts, 8 kilowatts is 8,000 watts. That means it's 1,000 joules per second that it's transferring, and this would be 8,000 joules per second that it's transferring. So if you imagine you had motor A, or another appliance that has a power rating is a microwave. I'm sure you've all used microwaves. And this would be motor B, or microwave B. You can see that this one has a much higher power rating. It's transferring much more energy per second. So if it was a motor, it'd be able to lift something faster or move something further. And a microwave would be able to cook. Microwave B would be able to cook your food much quicker. Okay? Now, just on this, I wanted to talk about efficiency. So efficiency is to do with energy transfer or power transferred, and it's basically a measure of what proportion of total energy or total power is usefully transferred. So the more energy that you input that is usefully transferred, the more efficient something is. And there's an equation for this as well. There's 2 versions, but I'm just going to put useful over total. Now that will give you a decimal. If you multiply that by 100, you will get a percentage. Now sometimes we see these diagrams called Sankey diagrams. So if you were putting 100 joules in, they look a bit like big arrows. Let's say I had 80 joules that was useful, then I know that I would have to have 20 joules that was wasted, because what you put in has got to be equal what's output totally, and that links back to your conservation of energy here. Okay, now ways that we can improve useful and reduce wasted include lubrication. Now that reduces friction. We can use insulation. So that reduces conduction, which is often how energy is dissipated to the surroundings. And you can actually tighten moving parts. So if you tighten them, they're going to move in the plane that you want them to move and not in ones that you're not interested in. And this insulation, that is also covered in another of the required practicals. Okay, so the final thing we're going to do is energy transfers. We've got 1 minute, energy resources. So energy resources, there are 2 types that you need to know. We've got renewable and we've got non-renewable. Now renewable, these are things that naturally replenish in a short time. So my handwriting's getting bad, but I want to get it done in a minute. And non-renewable, these do not replenish quickly or at all. So examples of renewable, you've got solar, you've got wind, wave, tidal, biomass, geothermal, and hydroelectric. Non-renewable, you've got your fossil fuels, which are coal, oil, and gas, and you've got nuclear. Okay. Now, you can be asked lots of questions on this to compare them, advantages, disadvantages, and the things that you need to talk about are usually the reliability. So does it work all the time? You need to know what it costs, and that's how much it costs to build, how much it costs to run it. You need to know what the energy output is, because if the energy output is low, you're obviously going to need a lot of it, and that can be quite costly. And you need to know the environmental impact. Environmental impact. So this could be things like, is carbon dioxide released? Does it produce any waste? Is it visual pollution, like wind turbines, etc.? Does it make a noise? Is it noise pollution? And these will be the sort of things that you're going to compare them on. Now, the other thing you need to know, this is the last thing I'll do, is that the energy use of the population over time has increased. The reason for that is that there are more people. So with more people on the earth, with higher energy consumption, we obviously need to produce more energy to meet those needs, and these sort of things start becoming important. Okay, so that's 11 minutes, not too bad. Hopefully that was useful.